Well, today we're going to learn about something quite amazing. We're going to sort of understand what we mean by a program a little bit more profoundly than we have up till now. Up till now, we've been thinking of programs as describing machines. So, for example, looking at this still store, what we see here is a program for factorial, and what it is a character string description, if you will, of the wiring diagram of a potentially infinite machine. And we can look at that a little bit and just see the idea that this is a sort of compact notation which says if n is 0, the result is 1. Well, here comes n coming into this machine, and if it's 0, then I control this switch in such a way that the switch allows the output to be 1. Otherwise, it's n times factorial of n minus 1. Well, I'm computing factorial of n minus 1 and multiplying that by n, and in the case that it's not 0, the switch makes the output come from there. Of course, this is a machine with a potentially infinite number of parts because factorial occurs within factorial, so we don't know how deep it has to be. But that's basically what our notation for programs really means to us at this point. It's a character string description, if you will, of a wiring diagram that could be also drawn some other way. And in fact, many people have proposed to make programming languages look graphical like this. I'm not sure I believe that there are many advantages. The major disadvantage, of course, is that it takes up more space on a page, and therefore it's harder to pack into a listing or to edit very well. But in any case, you know, there's something very remarkable that can happen in the computation world, which is that you can have something called a universal machine. If we look at the second slide, what we see is a special machine called eval. There is a machine called eval, and I'm going to show it to you today. It's very simple. What is remarkable is that it will fit on the blackboard. Okay. However, eval is a machine which takes as input a description of another machine. It could take the wiring diagram of the factorial machine as input. Having done so, it becomes a simulator for the factorial machine such that if you put a 6 in, out comes a 720. That's a very remarkable sort of machine. And the most amazing part of it is that it fits on a blackboard. By contrast, one could imagine in the analog electronics world a very different machine, a machine which also is in some sense universal, where you gave a circuit diagram as one of the inputs, for example, of this little low-pass filter, one-pole low-pass filter, and you could imagine that you could, for example, scan this out. The scan lines, right, are the signal that's describing what this machine is to simulate. Then the analog eval, which is made out of electrical circuits, should configure itself into a filter that has the frequency response specified by the circuit diagram. That's a very hard machine to make, and surely there's no chance that I could put it on a blackboard. So we're going to see an amazing thing today. We're going to see on the blackboard the universal machine. And see, among other things, it's extremely simple. Now, we're getting very close to the real spirit in the computer at this point. So I have to show it a certain amount of reverence and respect. So I'm going to wear a suit jacket for the only time that you'll ever see me wear a suit jacket here. Okay? And I think I'm also going to put on an appropriate hat for the occasion. Okay? Now, this is a lecture which I have to warn you, let's see, normally people under 40 and who don't have several children are advised to be careful, and if they're really worried, they should leave. Because there's a certain amount of mysticism that will appear here, which may be disturbing and cause trouble in your minds. Well, in any case, let's see. I wish to write for you the evaluator for Lisp. Now, the evaluator isn't very complicated. It's very much like all the programs we've seen already. That's the amazing part of it. It's going to be, and I'm going to write it right here, It's a program called eval. And it's a procedure of two arguments, an expression and an environment. And like every interesting procedure, it's a case analysis. But before I start on this, I want to tell you some things. The program I'm going to write on the blackboard is ugly, dirty, disgusting. Not the way I would write this as a professional. Okay? It is written with concrete syntax, meaning I'm going to use lots of cars and cooters, which is exactly what I told you not to do. That's on purpose in this case, because I want it to be small, compact, fit on the blackboard so you could get the whole thing. So I don't want to use long names like I normally use. Okay? I want to use car cooter because it's short. Okay, there's a whole, that's a trade-off. Now, I don't want you writing programs like this. This is purely for an effect. Okay, now you're going to have to work a little harder to read it, but I'm going to try to make it clear as I'm writing it. This is a pretty much complete interpreter, but there's going to be room for putting in more things. I'm going to leave out definition and assignment, just because they're not essential for a mathematical reason that I'll show you later, and also they take up more space. But in any case, what do we have to do? Well, we have to do a dispatch, which breaks the types of expressions up into particular classes. So that's what we're going to have here. Well, what expressions are there? Let's look at the kinds of expressions. We can have things like the numeral 3. What do I want that to do? I can make choices, but I think right now I want it to be a 3. That's what I want. Okay, so that's easy enough. That means I want, if the thing is a number, the expression, then I want the expression itself as the answer. Okay? Now the next possibility is things that we represent as symbols. Examples of symbols are things like exp, env, eval, number, x. What do I mean them to be? Those are things that stand for other things. Those are the variables of our language. Okay, so I want to be able to say, for example, that x, for example, transforms to its value, which might be 3. Okay, or I might have something like car. I want to have as its value be something like some procedure. Which I don't know what it is inside there. Perhaps some machine language code or something like that. Okay, so, well, that's easy enough. I'm going to push that off on someone else. If something's a symbol, if the expression is a symbol, then I want the answer to be the result of looking up the expression in the environment. Now, the environment is a dictionary which maps the symbol names to their values. And that's all it is. How it's done, well, we'll see that later. Okay, it's very easy. It's easy to make data structures that are tables of various sorts. But it's only a table, and this is the access routine for some table. Okay. Well, the next thing, another kind of expression. You have things that are described constants that are not numbers, like foo. Well, for my convenience, I want to syntactically transform that into a list structure which is quote foo. Or it's a quoted object, whatever it is going to be actually an abbreviation, which is not part of the evaluator, okay, but happens somewhere else. An abbreviation for an expression that looks like this. This way I can test for the type of the expression as being a quotation by examining the car of the expression. Okay? So I'm not going to worry about that in the evaluator. It's happening somewhere earlier in the reader or something. If the expression of the expression is quote, then what do I want? I want quote foo to itself evaluate to foo. It's a constant. This is just a way of saying that this evaluates to itself. Okay, so that's the, what is that? That's the first of the second of the list. It's the second element of the list. Okay, but the second element of the list is its catter. So I'm just going to write here catter. Okay, what else do we have here? We have lambda expressions. For example, lambda of x, lambda x plus xy. Well, I'm going to have some representation for the procedure, which is the value of an expression, of a lambda expression. The procedure is not the expression lambda x. That's the description of it, the textual description. However, what I'm going to expect to see here is something which contains an environment as one of its parts. Right? If I'm implementing a lexical language. And so what I'd like to see is some type flag, because I'm going to have to be able to distinguish procedures later, procedures which were produced by lambdas from ones that may be primitive. And so I'm going to have some flag which I'll just arbitrarily call closure just for historical reasons. Now I have to say what parts of this are important. I'm going to need to know the bound variable list and the body. Well, that's the cdr of this. So that's going to be x and plus xy and some environment. Now this is not something a user should ever see. This is purely a representation internally for a procedure object. It contains a bound variable list, a body, and an environment. And some type tag saying I am a procedure. I'm going to make one now. So if the car of the expression is, quote, lambda, then what I'm going to put here is I'm going to make a list of closure, the cdr of the procedure description, which is everything except the lambda, and the current environment. This implements the rule for environments in the environment model. It has to do with construction of procedures from lambda expressions. The environment that was around at the time the evaluator encountered the lambda expression is the environment where the lambda expression gets, where the procedure resulting interprets its free variables. So that's part of that, and so we have to capture that environment as part of the procedure object. And we'll see how that gets used later. There are also conditional expressions, things like cond of, say, P1, E1, P2, E2, where there's a predicate, and this is a predicate is a thing that's either true or false, and an expression to be evaluated if the predicate is true. A set of clauses, if you will. That's the name of such a thing. So I'm going to put that somewhere else. We're going to worry about that in another piece of code. So EQ, if the car of the expression is cond, then I'm going to do nothing more than evaluate the cond, the cdr of the expression. That's all the clauses in the environment that I'm given. Well, there's one more case. Arbitrary thing like the sum of x and 3. Where this is an operator applied to operands. And there's nothing special about it. It's not one of the special cases. The special forms. These are the special forms. And if I were writing here a professional program again, I would somehow make this data directed So there wouldn't be a sequence of conditionals here. There'd be a dispatch on some bits. Okay, if I were trying to do this in a more professional way, so that in fact I could add to the thing without changing my program much. So for example, the thing would run fast. But I'm not worried about that. Here we're trying to look at this in its entirety. So it's else. Well, what do? In this case, I have to somehow do an addition. Well, I have to find out what the plus is, and I have to find out what the x and the 3 are. And then I have to apply the result of finding out what the plus is to the result of finding out what the x and the 3 are. Okay, we'll have a name for that. So I'm going to apply the result of evaluating the car of the expression. The car of the expression is the operator. In the environment given, so evaluating the operator gets me the procedure. And now I have to evaluate all the operands to get the arguments. I'll call that evlist. The coulter, that's the operands of the expression with respect to the environment. Evlist will come up later. Evlist, apply, cond pair, cond, lambda define. Okay? So that what you're seeing here now is pretty much all there is in the evaluator itself. It's the case dispatch on the type of the expression with the default being a general application or a combination. Now there's lots of things we haven't defined yet. Let's just look at them and see what they are. We're going to have to do this later, evcond. We're going to have to write apply. We're going to have to write evlist. We're going to have to write lookup. I think that's everything, isn't there? Everything else is something which is simple or primitive or something like that. Okay? And of course, we could put many more special forms here, but that would be a bad idea in general in a language. You make a language very complicated by putting a lot of things in there. The number of reserved words that should exist in a language should be no more than a person can remember on his fingers and toes. And I get very upset with languages which have hundreds of reserved words. But that's where the reserved words go. Okay. Well, now let's get to the next part of this, the kernel, apply. Okay. What else is this doing? Well, apply's job is to take a procedure and apply it to its arguments after both have been evaluated to come up with the procedure and the arguments rather than the operator symbols and the operand symbols, whatever they are, symbolic expressions. So we will define apply to be a procedure of two arguments, a procedure and arguments. And what does it do? It does nothing very complicated. It's got two cases. Either the procedure is primitive, and I don't know exactly how that is done. It's possible that there's some type information, just like we made closure for here being the description of the type of a compound thing. Okay? Probably so. But it's not essential how that works. And in fact, it turns out, as you probably know or have deduced, that you don't need any primitives anyway. You can compute anything without them, because of some of the lambda playing that I've been playing with. But it's nice to have them. So here we're going to do some magic, which I'm not going to explain. Go to the machine language. Apply primop. Here's how it adds. Execute an add instruction. However, the interesting part of a language is the glue by which the primitives are glued together. So let's look at that. Well, the other possibility is that this is a compound made up by executing a lambda expression. This is a compound procedure. Well, we'll check its type. If it is, closure. If it's one of those, then I have to do an eval of the body, right? The way I do this, the way I deal with this at all, is the way I evaluate the application of a procedure to its arguments is by evaluating the body of the procedure in the environment resulting from extending the environment of the procedure with the bindings of the formal parameters of the procedure to the arguments that were passed to it. Long sentence. Well, that's easy enough. However, here's going to be a lot of charcuterie. I have to get the body of the procedure. Where's the body of the procedure? In here. Well, here's the car. Here's the cutter is the whole rest of this. So here's the catter. And so I see what I have here is the body is the second element of the second element of the procedure. So it's the catter of the catter or the catter-datter. It's the C-A-D-A-D-R. Cadatter of the procedure. So I evaluate the body. In the result of binding, that's making up more environment. Well, I need the formal parameters of the procedure. What is that? That's the car of the catter. Okay? It's horrible, isn't it? Of the procedure. Bind that to the arguments that were passed in the environment which is passed also as part of the procedure. Well, that's the car of the cutter of this. Cateter. Of the procedure. Bind, eval, pair, cond, lambda, define. Okay? Now, of course, if I were being really a neat character and I was being very careful, I would actually put in an extra case here for checking for certain errors, like did you try to apply one to an argument? You get a undefined procedure type. So I may as well do that anyway. Else, some sort of error. Okay? Like that. Now, of course, again, in some sort of more real system, written for professional reasons, this would be written with a case analysis done by some sort of dispatch. Over here, I would probably have other cases like, is this compiled code? It's very important. I might have to distinguish the kind of code that's produced by directly evaluating a lambda in an interpretation from code that was produced by somebody's compiler or something like that. And we'll talk about that later. Or is this a piece of Fortran program I have to go off and execute? And it's a perfectly possible thing at this point to do that. In fact, in this concrete syntax evaluator I'm writing here, there's an assumption built in that this is Lisp. Right? Because I'm using cars and cutters. Car means the operator, and cutter means the operands. In the text, there's an abstract syntax evaluator for which these could be, are given abstract names like operator and operand and all these other things like that. And in that case, you could reprogram it to be algol with no problem. Okay, well here we have added another couple of things that we haven't defined. I don't think I'll worry about these at all. However, this one will be interesting later. Well, let's just proceed through this and get it done. And there's only 2 more blackboards, so it can't be very long. Okay? It's carefully tailored to exactly fit. Well, what do we have left? We have to define evlist, which is over here. And evlist is nothing more than a map down a bunch of arguments, operands, producing arguments. But I'm going to write it out. And one of the reasons I'm going to write this out is for a mystical reason, which is I want to make this evaluator so simple that it can understand itself. Okay. I'm going to really worry about that a little bit. So let's write it out completely. See, I don't want to worry about whether or not the thing can pass functional arguments. The evaluator is not going to use them. The evaluator is not going to produce functional values. So even if there were a different alternative language that were very close to this This evaluates a complex language-like scheme, which does allow procedural arguments, procedural values, and procedural data. But even if I were evaluating algol, which doesn't allow procedural values, I could use this evaluator. Okay, and this evaluator is not making any assumptions about that. And in fact, if this evaluator were restricted to not being able to do that, it wouldn't matter because it doesn't use any of those clever things. So that's why I'm arranging this to be super simple. This is sort of the kernel of all possible language evaluators. How about that? evlist. Well, what is it? It's a procedure of two arguments, L and an environment, where L is a list, such that if the list of arguments is the empty list, then the result is the empty list. Otherwise, I want to const up the result of evaluating the car of the list of operands in the environment. So I want the first operand evaluated, and I'm going to make a list of the results by consting that onto the result of evlisting. So it's a Kutter recursion, the Kutter of the list relative to the same environment. Evlist, const, else, cond, lambda, define. Okay? And I have one more that I want to put on the blackboard. So it's the essence of this whole thing. And then there's some sort of next layer down. Conditionals. Conditionals are the only thing left that are sort of substantial. Then below that, we have to worry about things like lookup and bind. And we'll look at that in a second. But of the substantial stuff at this level of detail, the next important thing is how you deal with conditionals. Well, how do we have a conditional thing? Okay. It's a procedure of a set of clauses and an environment. And what does it do? It says, if I have no more clauses, well, I have to give this a value. It could be that it was an error. Supposing I run off the end of a conditional. It's pretty arbitrary. It's up to me as a programmer to choose what I want to happen. It's convenient for me right now to write down that this has a value, which is the empty list. Doesn't matter. Right? For error checking, some people might prefer something else. But the interesting things are the following ones. If I've got an else clause, see, if I have a list of clauses, then each clause is a list. And so the predicate part is the KR of the clauses. It's the car, which is the first part of the first clause in the list of clauses. Okay? If it's an else, then it means I want my result of the conditional to be the result of evaluating the matching expression. So I eval the catter. So this is the first clause, the second element of it, catter of the car, okay, of the clauses with respect to the environment. Now, the next possibility is more interesting. If it's false, if the first predicate in the predicate list is not an else and it's not false, if it's not the word else, and if it's not a false thing, let's write down what it is if it's a false thing. If the result of evaluating the first clause, first predicate, the clauses with respect to the environment, if that evaluation yields false, then it means I want to look at the next clause. So I want to discard the first one. So we just go around the loop, evcond, the Kutter of the clauses, relative to that environment. And otherwise, I had a true clause, in which case what I want is to evaluate the cat-r of the clauses relative to that environment. Boy, it's almost done. It's quite close to done. I think we're going to finish this part off, sort of just buzzing through this evaluator. But so far, you're seeing almost everything. Let's look at the next transparency here and see, yes, here is bind. Bind is for making more table. And what we're going to do here is we're going to make a new frame for an environment structure. The environment structure is going to be represented as a list of frames. So given an existing environment structure, I'm going to make a new environment structure by constantly a new frame onto the existing environment structure, where the new frame consists of the result of pairing up the variables, which are the bound variables of the procedure I'm applying, to the values, which are the arguments that were passed to that procedure. So this is just making a list. I was adding a new element to a list of frames, which is an environment structure, to make a new environment. Okay. Where pair up is very simple. Pair up is nothing more than if I have a list of variables and a list of values. Well, if I've run out of variables and if I've run out of values, everything's okay. Otherwise, I'm given too many arguments. If I've not run out of variables but I've run out of values, then I have too few arguments. And in the general case where I don't have any errors and I'm not done, okay, then I really am just adding a new pair of the first variable with the first argument, okay, the first value, onto a list consisting of resulting from pairing up the rest of the variables with the rest of the values. Lookup is, of course, equally simple. Right? If I have to look up a symbol in an environment, well, if the environment is empty, then I've got an unbound variable. Otherwise, what I'm going to do is use a special pair list lookup procedure, which we'll have very shortly, of a symbol in the first frame of the environment. Since I know the environment is not empty, it must have a first frame. So if I look up the symbol in the first frame, that becomes the value cell here. Okay? And then if the value cell is empty, okay, if there is no such value cell, then I have to continue and look at the rest of the frames. It means there was nothing found there. So that's a property of ASCII, is it returns emptiness if it doesn't find something. Okay? But if it did find something, then I'm going to use the cdr of the value cell here, which is the thing that was the pair consisting of the variable and the value. So the cdr of it is the value part. Okay? Finally, ASCII is something you probably have seen already. ASCII takes a symbol and a list of pairs, and if the list is empty, it's empty. If the symbol is the first thing in the list, that's an error. That should be CAAR, C-A-A-R. Everybody note that. Right there. Okay? And in any case, if the symbol is the KR of the A list, then I want the first pair in the A list. So in other words, if this is the key matching the right entry. Otherwise, I want to look up that symbol in the rest. Sorry for producing a bug. Okay, bugs appear. Well, in any case, you've pretty much seen the whole thing now. Okay? It's a very beautiful thing, even though it's written in an ugly style, being the kernel of every language. I suggest that we let's look at it for a while. Are there any questions? All right, I suppose it's time to take a small break then.